Good morning, dear students. Today we are going to discuss about the topic energy stored in a magnetic field. We already see the topic Faraday's law of electromagnetic induction. According to Faraday's law of electromagnetic induction, induced EMF is directly proportional to negative time rate of change of magnetic flux. Epsilon is equal to minus d phi by dt. Here phi is the magnetic flux. Okay, and we know the magnetic flux phi is equal to surface integral B dot ds. Here B is the magnetic field, ds is the small area. So from this, from equation 2 we can find that phi is proportional to B if ds is constant. If area is constant, you can say the flux, magnetic flux, is directly proportional to the strength of magnetic field B. Okay. And according to Biot-Savart's law, the magnetic field B is proportional to current. Magnetic field B is proportional to current according to Biot-Savart's law. Okay. So when the current in the coil is increased, magnetic field also increases. When the magnetic field increases, flux phi is also increasing. This this flux is changing. That means it will induce an EMF. Okay. So this time varying magnetic field induces an electric field. This time varying magnetic field induces an electric field. Okay. So this exerts some force on that electric charges. This electric field exerts force on electric charges, and that results in a current. Okay. And according to Lenz's law, the induced current will oppose the change in magnetic flux. Okay. So according to Lenz's law, nature abhors the change. So the system will try to reduce, or that induced current will try to reduce the current flow. Okay. So initially there was a current which is increasing, and that results in a magnetic field, increase in magnetic field, and that increase in magnetic field results in a change in magnetic flux, and that will result in an induced EMF. This induced EMF induces a current, and that current opposes that increase in initial current. Okay. So if you want to maintain a constant current through that circuit, we have to do, or some external agency has to do some work on that system. Okay. So to maintain the current flow, work is to be done by external voltage source. Okay. And this must be against that induced electric field. This work done is stored as potential energy. Okay. So in order to maintain a constant current flow in that circuit, the external voltage source has to do some work. This work is stored as potential energy. This is the energy stored in a magnetic field. This is the energy stored in magnetic field. Now we have to obtain the equation or the mathematical representation for this amount of work done. Okay. So, we know EMF. EMF is the work done to move a unit positive charge once along a closed path. So, you can write W is equal to minus epsilon. W is equal to minus epsilon. Okay. This epsilon is induced EMF. Actually, epsilon is the induced EMF, and we have to do work against that induced EMF. Okay. Suppose I is the current flowing through that circuit. When I is the current flowing through that circuit, or we want to maintain this current I, then work done per unit time dW by dt is equal to minus epsilon I. Work done by unit time is equal to minus epsilon I. Okay. And we know epsilon is equal to minus d phi by dt from this equation number 1. Sorry, this is not, this is equation number 1. Substitute this equation number 1 in 6, then dW by dt can be written as d phi by dt into I. Okay. And we already studied that phi is equal to Li, where L is the self inductance. So, substitute this 8 in equation number 7, then dW by dt is equal to d by dt of Li into I. Okay. So, if you want to calculate what is the net work done to increase current from 0 to I, W is equal to net work done, total work done is equal to, W is equal to integral dW. Okay, that is equal to integral, L is a constant, I is, this I is already outside that differential, and then only di by dt, like this. This I is here, dLi by dt is here. From this L is taken outside, then I into L di by dt, okay, which is used here. Here not dt is not required because this dW by dt, then you have to write di by dt. Here only dW is written on the left hand side, so no need of dt. Okay. So, here L is taken as constant outside, integral I di, which is nothing but I square by 2. So, W is equal to L I square by 2. Here current is starting from 0 to I. So, W is equal to half L I square, which is the expression for work done. Okay. So, this is the work done and this is the energy stored in magnetic field. Okay. And this is in terms of current. Okay. We can also write this expression for work done in terms of magnetic field also. Okay. So, we have to write this work done in terms of magnetic field. Okay. For that, we know phi is equal to integral B dot ds. So, just again put this equation number 9, it is a very important equation, and we are using again a previous equation, phi is equal to integral b dot ds, which is given by equation number 2, given as equation number 2. Okay, and we know b is equal to del cross a, which is equation number, what is that? It's not 9, it's 10. Okay, and substitute this 10 in equation number 2, that is phi is equal to integral del cross a dot ds. So this is the integration over surface integral or area, and we have to convert it into line integral. Okay, for that we can use Stokes theorem. According to Stokes theorem, surface integral del cross f dot ds must be equal to line integral f dot dl. So in the same sense, we are using we are applying Stokes theorem here, and the result is like this: phi is equal to, instead of surface integral we will get line integral, closed line integral a dot dl. Okay, and we also know from our previous section, or we are equation number 8, phi is equal to li. Okay, we got this equation, which is equation number 11, and we already know phi is equal to li, which was our equation number 8. Okay, so since equation number 8 and equation number 11 both for both left hand sides is equal, which is magnetic flux phi, so we can equate the right hand sides. Okay, equate RHS both equations, then you can write li is equal to closed line integral a dot dl. Okay, now we know work done is equal to half li square from equation number 9. So this is equation number 12. Equation number 9 is w is equal to half li square. I am rewriting this as half I into li. Okay, so this is used here, half I into, instead of li substitute this, line integral a dot dl. You can take the current inside the integral, and we can write this as half integral a dot I dl. Here the current is taken as a vector, a dot I dl. Okay, so this is the expression for work done, half closed line integral a dot I dl. Since the current flows along the direction of dl, like this, if this is the circuit, if this is the closed path and dl is along this length, then current is also flowing in this sector. Okay, so dl and I are in same direction, so you can write I into vector dl is equal to vector I dl. Okay, now this is for line current density. You can convert this into surface current density. W is equal to half, instead of line integral you will get volume integral a dot, instead of line current density you can use j d2. Okay, here j is the j is given by, we know our equation, some equation you may be familiar with, del cross b is equal to mu 0 j. From this this is 13, this is 14. Okay. From this j is equal to del cross b by mu 0. Okay, we can use this here, equation number 15 in 14. So w is equal to half volume integral a dot del cross b by mu 0 d2. Okay, this mu 0 is a constant, you can take it outside that integral, then it will be 1 by 2 mu 0 volume integral A dot del cross B d2. Okay, now this is the expression for work done that we have got, which is equation number 16, and there is a formula del dot A cross B. Okay, this can be written like this: B dot del cross A minus A dot del cross B. Okay, B dot del cross A minus A dot del cross B. Okay, from equation number what is B equal to del cross A? From equation number 10, you can it is found that del cross A is equal to B. Here there is a del cross A. For that, just put B. So B dot B minus A dot del cross B. Okay, and look at this. There is a term inside our bracket, A dot del cross B. Here is the A dot del cross B. Okay, so you have to write A dot del cross B from this equation, and you will get that. Take A dot del cross B to the left, so it will be plus A dot del cross B. B dot B is nothing but B square, and take del dot A cross B to the right, then it will be minus del dot A cross B. Okay, so you can substitute this equation number 17 in 16. Okay, then W will be equal to 1 by 2 mu 0 is there, volume integral is there. Instead of A dot del cross B, put B square minus del dot A cross B d2. Okay, so we can separate this integration into two: 1 by 2 mu 0, which is common for all, then volume integral B square d2 minus volume integral del dot A cross B d2. Okay, here in the second part we are using divergence theorem. Okay, according to divergence theorem, del dot F d2, volume integral del dot F d2 is equal to surface integral F dot ds. Okay, we are using this in above equation, especially in equation number 18, that is substitute 19 in 18, then you can write W is equal to 1 by 2 mu 0, which is again commonly outside, volume integral B square d2 is there, minus surface integral A cross B dot ds. Okay, so this is the expression for work done that we have got, which is equation number 20. Okay, and we already wrote some equation. W is equal to 1 by 2 volume integral A dot J d2 from equation number 9. Sorry, it's equation number 14. Okay, so W is equal to 1 by 2 volume integral A dot J d2, which was equation number 14. On comparing this 14 and 20, left hand sides are same, so we can equate the right hand sides. Okay, so you will get 1 by 2 volume integral A dot J d2 is equal to 1 by 2 mu 0 volume integral B square d2 minus surface integral A cross B dot ds. Okay, here left hand side is a constant because it is the volume integral over the whole surface. Okay, so if you are considering more and more of the space, or if you are expanding into the whole space, the contribution from surface integral decreases. Okay, and contribution from the volume integral of that RHS increases. So if you are considering more and more space, or if you are considering the whole space, then the volume integral contributes, and the contribution from surface integral is decreased and it will become negligibly small. Okay. So, for the entire volume, for the whole volume, W is equal to 1 by 2 mu 0 for all space B square d2 will be the work done. Okay. So, this is for all space. This is the work done. Then what is the work done per unit volume? If you are considering work done per unit volume, or which is the energy, this is the energy stored. Work done is nothing but it is the energy stored in magnetic field. Okay, expression of energy stored in magnetic field is given by W is equal to 1 by 2 mu 0 B square d2. This is for all space, otherwise you can write this equation, above equation. Okay. So, now what is, this is the work done, or which is the energy stored in magnetic field. Okay. Now, what is meant by energy density? Energy density means energy per unit volume. Okay. Or you can write work done per unit volume. Okay. So, that will be equal to, energy density will be equal to B square by 2 mu 0, because integral over whole space d tau is nothing but it is the volume. Okay. So, W by volume means the only term is B square by 2 mu 0. Okay. So, B square by 2 mu 0 will be the energy density from this equation, and if you are considering this one, energy density will be remove the volume integral and d tau, the remaining term will be the energy density, that is 1 by 2 A dot J will be the energy density. Okay. So, we have already seen the term for energy density, electric. Energy density in electric field, that is in our previous papers, that is 1 by 2 V rho, or half epsilon 0 E square, and energy density in magnetic field, it is 1 by 2. Here V is the volume, here V is the electric potential, in this case it is the magnetic potential. Here rho is the charge density, here it is the current density. Okay, so you can compare this, half is there, V is electric potential. So, in the same sense this is magnetic potential. Here it is charge density, the same, this is current density. Okay. In the same sense, half B square by mu 0. Here also half is there. Here E in the above equation, for the energy density for electric field, E is the electric field, here it is B magnetic field. Here instead of epsilon 0, which is permittivity of free space, here 1 by mu 0, which is the permeability of free space. 1 by mu 0 is not permeability, mu 0 is the permeability of free space, and instead of epsilon 0 you just put 1 by mu 0. Okay. So, this is the expression for energy density, half epsilon 0 E square for electric field, and half B square by mu 0 is for the magnetic field. Okay. Thank you.